Breakthrough quantum computer processor from IBM has 3 times more qubits than previous quantum computing technology. IBM's latest quantum computer processor marks a huge step forward for its ambitions in the field. At the IBM Quantum Summit 2022, the company announced Osprey, which has the largest qubit count of any of its processors at 433 quantum bits. That's more than triple the number of qubits that the Eagle quantum computing chip has. IBM said it built on top of the 127-qubit Eagle's architecture by keeping qubits on a single plane with the help of multi-level wiring. Unlike classical bits with a state of 1 or 0, qubits exist in a complex mix of both and tap into the quantum physics of matter at subatomic levels. As a result, quantum computers offer the possibility of vastly increased computing power to tackle calculations of much greater complexity in fields like artificial intelligence or designing new materials for drug discovery and energy research. The company is scaling up its quantum computing efforts with the aim of building a system with 4,000 plus qubits by 2025, and it's currently on target with its roadmap. Next up is a 1,121 qubit chip called Condor, which IBM hopes to unveil next year. IBM showed an elegant and functional quantum computer at CES 2019. Last year, it offered a sneak preview of the design for the next-gen IBM Quantum System 2, the machine that will use its quantum processors. Now, the company has revealed more details. It designed the system to be flexible and modular with the ability to house multiple architectures and processors, and claims it will include Osprey starting next year. The company claimed the System 2 design allows for an exponential step-up in quantum computing scale and enabling the vision of quantum-centric supercomputing. Having immense computational power at one's fingertips doesn't mean much if you don't have the right software to get the most out of it. Early last year, IBM said that its Scikit program execution environment was able to blend quantum and conventional computers to carry out complex computations in hours, when they previously would have taken months. The company said it will offer new features to mitigate and suppress errors and provide a fast, efficient, and easy-to-use programming model for quantum computers. What's more, these features blend into IBM's goal of integrating quantum computers with classical computers, including supercomputers. Scientists build the first crucial components of a molecular computer. As scientists learn more about life's machinery, they're beginning to take the controls. Genetic engineers are tweaking the code with gene editing tools to treat illness. Synthetic biologists are coaxing genetically modified bacteria into producing substances like biofuels or converting society's waste into valuable chemicals. Still more researchers are aiming to use DNA for digital storage and even robotics. In the researchers' latest work published in Nature, they've taken a crucial step toward the ultimate goal: working molecular computers. If fully realized, the researchers' vision would bring about a new way to build and compute. Molecular computers could store data and, like ribosomes, assemble physical products from coded blueprints. Instead of stringing amino acids into proteins, they might produce finely tuned materials with new properties that would be impossible to make any other way. The research team says they've built the first components of a molecular computer, a coded molecular ribbon and a mobile molecular reader of the code. These molecular machines have a few key parts: a segmented molecular ribbon with carefully designed docking sites, a molecular ring that binds to and travels along the ribbon, and a solution in which many copies of the system are afloat. The research team fuels the system with pulses of acid, which changes the solution's pH and modifies the ribbon structure. With the first pulse, free molecular rings composed of a crown ether or a ring of ether groups thread themselves onto the ribbons, docking at the first of several binding sites. Each binding site's chemical makeup induces a stereochemical change in the crown ether. That is, the binding site modifies the crown ether's orientation in space without changing its composition. Additional pulses of acid move the crown ether along sequential binding sites, and each new site causes it to contort itself into a different encoded configuration. These stereochemical changes are the key. The team assigned each configuration a value. Instead of the ones and zeros in binary code, they chose negative ones, zeros, and positive ones for two stereochemical twists, each the mirror of the other in a neutral position. So, as the crown ether traverses the molecular ribbon, its chemical changes read out the code. Each crown ether configuration twists the light differently. By baiting the solution in light, they could watch the changes as they took place. The team found the twisting light matched the crown ether's journey along the ribbon, broadcasting the message exactly as encoded. The system is slow, takes several hours to move from site to site, only reads in one direction, and can't yet write information, so there is a great deal of work ahead. But it's still a step in the right direction, and the next steps are in the works. The research team plans to get the system to write data. They think greater speed is possible, while perhaps being less important for some applications, and they might increase information density by going from a 3-digit system to 5 or even 7 digits. As scientists build on this work, they may open up a parallel universe of synthetic molecular computing machines just adjacent to the organic world, creating elements like computronium. Researchers develop a material that mimics how the human brain stores information. Universitat Autònoma de Barcelona researchers have developed a magnetic material capable of imitating the way the brain stores information. The material makes it possible to emulate the synapses of neurons and, for the first time, mimics the learning that occurs during deep sleep. Neuromorphic computing is a new computing paradigm in which the behavior of the brain is emulated by mimicking the main synaptic functions of neurons. Among these functions is neuronal plasticity, the ability to store information or forget it depending on the duration and repetition of the electrical impulses that stimulate neurons, a plasticity that would be linked to learning and memory. The researchers have proposed a new way of controlling the evolution of magnetization both in the stimulated and in the post-stimulus states. The researchers have developed a material based on a thin layer of cobalt mononitride, where by applying an electric field, the accumulation of N ions at the interface between the layer and a liquid electrolyte in which the layer has been placed can be controlled. The new material works with the movement of ions controlled by electrical voltage, in a manner analogous to our brain, and at speeds similar to those produced in neurons of the order of milliseconds. The researchers have developed an artificial synapse that in the future may be the basis of a new computing paradigm, alternative to the one used by current computers. By applying voltage pulses, it's possible to emulate processes like memory, information processing, information retrieval, and, for the first time, the controlled updating of information without applied voltage by modifying the thickness of the cobalt mononitride layers, which determines the speed of the ion's motion and the frequency of the pulses. The arrangement of the material allows the magnetoionic properties to be controlled not only when the voltage is applied, but also, for the first time, when the voltage is removed. Once the external voltage stimulus disappears, the magnetization of the system can be reduced or increased, depending on the thickness of the material and the protocol of how the voltage has been previously applied. This new effect opens a whole range of opportunities for new neuromorphic computing functions. It offers a new logic function that allows, for example, the possibility of mimicking the neural learning that occurs after brain stimulation, when we sleep profoundly. This functionality cannot be emulated by any other type of existing neuromorphic materials.